I don't know if you've ever noticed, but if you turn the gain way down when the steering is pretty close to the line, how much better it behaves. And just to limit the speed of the motor instead of it oscillating back and forth and working quickly. But then you get to a U-turn and the thing doesn't turn fast enough. And you go past the U-turn and that just makes a mess. So this just happened by accident. I've been thinking about this for a long time, but never figured out how to actually do it. Was to be able to have that dual speed sort of feed forward method where you can slow the motor down as it gets to the air gets to zero, but yet still have enough proportional gain. Now you can use that with proportional gain, but as you know, the motor just dies out and never makes it to the line. You can still have lots of proportional gain, but the thing doesn't go crazy as it gets towards zero, like in terms of zero error. So more of a controlled sort of speed control along with the proportional gain. That basically is called feed forward, having the intelligence to slow the motor down without using a differential term because it's so noisy in a GPS setting, but to be able to slow that motor down intuitively and be able to set those on the fly. Now, you don't want to completely slow down the motor because then it stops, but you still want enough pulse width to keep that motor turning. Now, Wool we were talking a little bit this morning about whether or not the formula was right, and well, it is kind of right. Down here at the bottom, we have our minimum speed, like when the error is zero. This is error here, and then this is the max pulse width that gets sent to the motor. The lower the pulse width, the slower the motor goes. So if our error is really low, that means we're on the line where we should be. So then we want the maximum speed of that motor to be quite slow, no matter what the proportional gain is. And then as we move with more and more gain, more and more error, we want the motor to spin faster. And that's it. And as that error increases, our limit on how fast that motor can turn gets going much faster. Now you can imagine there's a lot of things that we can adjust here. So you can adjust, say, this down to 20 and that to 160, and the curve is steeper. The other thing potentially is to adjust how fast this comes in. Now I just chose 5. I have no idea how that works out in the field. We have so much snow and mud that there is no driving anywhere. But others can drive it. So maybe how quickly or how slowly that ramp comes in and out needs to be adjustable too. But right now it's set to 5, and there's a define in the Arduino code where you can change that and just change it in one place. Change it to 2, change it to 7. I don't know. But what we're after today is just this concept of slowing the motor down based on error. Okay, so we're back in our usual scene here again. Bring up the steer chart of this crazy pulse width modulated mess. And again, this is the wheel angle sensor and this is the motor, and I've disconnected the two so that we can move it around. Go back to the gain. Now our counts per degree, we'll set it to 50 or whatever. Again, that should flash. If that stays red, then the check is messed up. Then it's not communicating. It's not sending back what it is receiving. And you have a problem, and that needs to be fixed. Yeah, that's all okay. So in terms of proportional gain, minimum pulse width, HighMax and LowMax. Now that's different. This used to say dead zone, but just kind of repurpose that dead zone into something actually useful. The dead zone, it might have worked, I guess, but I think this is much, much better because now we have a dead zone that linearly ramps based up on our error. So proportional gain. So we'll turn this on, turn the drive on, and let's set our proportional gain to 10. Now it's a little less than half. So we didn't have no minimum pulse width modulation, like no minimum drive to the motor. So if we set it to 10, our PWM and an error of, well, almost 1, then we get 4. If we turn this to 20, we should have around 10. If we set this to 70, let's make this exactly 1. There. Then it's basically half. So we have an error of 1, we have 32. If we turn the error up to say 2, it's only 50. Why is it 50? Because we're limited on our max. So there, error of 2, our pulse width modulation is 70. 70 out of 255 of the time, the thing is on. So that's proportional gain. Now you crank it up to 200, it just zooms. So you can imagine at 200, if there's one error or 1 degree of error, then all of a sudden the pulse width modulation is up at 100. It adds 100 to it. Now we'll set this to 20. We'll set it to 40. So, okay. And we'll turn this back down to 1. Otherwise everything gets going too fast. There, see now our error, our actual is at -1 and our set point is at 0. That gives us an error of 1. Half of our gain, our proportional gain, ends up as our pulse width modulation. Now if we add minimum, say we add 10 to our minimum. Now instead of 20, it's almost 30. And it'll never go below that. So even if we turn down our proportional gain, turn that down to 20. Remember, half of 20 is 10. Our 10 stays. As we turn this guy up, it just keeps adding up. So it never goes below. So that's like a minimum. If we turn this guy to 0, and everything shuts off. Now it doesn't matter what you have anywhere. If the error is 0, then the pulse width modulation is going to be 0. So for that one brief moment in time between -1 and +1, everything is off. There is no minimum set. So turn this back up to 40. Turn this back up to 10. There, now our minimum is set at 10. Well, it's always going to be 1 more than 10, just the way it rounds up. But so that basically sets your proportional gain times the error. Take half of it if you want a rough idea, or just keep turning it up until your motor spins fast enough. The minimum pulse width, what you want to do is overcome the friction that the motor has. So if we turn this to 1, give it some air so that it actually turns on. You can see it's just barely turning. Turn it to 8. There, so it's about 6, 7 is about all it takes to turn that little motor. As we go higher, it turns faster. So you want to set that minimum so that it just barely turns, just to overcome the friction of the steering wheel and the motor itself and starting it. It's a very, very sensitive setting. Now, let's talk about maxes. Now remember, when our error is high, then we want to limit the speed of the motor based on the HighMax. As we're approaching 0 error, like as we get to 0, whoops, the wrong way. As we get to 0 error, we want we want to slow everything down. We want to slow the world down. So we set our LowMax. I'll set him to 10, a little higher, 20. And we'll set this one to, call it 80. So now as the error goes from 0 to 5 degrees, and supposing we have enough proportional gain, see, as we crank the gain up now, we're limited to, here we'll turn the error down. There, we're limited to our LowMax. If we turn this guy up to 80, so even though we have an error of 0.6, then the motor goes like crazy. But if we turn down our LowMax, then we limit the speed of the motor based on our error. So now we're going to use the low maximum pulse width. Again, this is the limit of the speed of the motor. So as our error increases, we're using more and more of that 20 to 100 range. So as the thing comes into line, it slows everything down. I mean, you got the steering wheel and the motor and everything spinning at 100 pulse width modulation limit. And then when you get onto the line, what's it supposed to do? It's supposed to just immediately stop. Well, it doesn't. It goes past, and then it goes, oh, I got to go the other way. So it takes that full 100 PWM and tries to spin it the other way. And then it goes past again, and then it tries to spin the other way, and it spins the other way. A much better way is to, as we approach the error of 0, let's slow the motor down so that it has a chance when it gets to 0 to use some of that proportional gain, and then just slow everything down, slow the world down. But if we do have a higher error, let's get there quickly. So I hope this concept makes sense. Again, I haven't tried it in the tractor, but what I'll do is I'll move the little connection to the wheel angle sensor over, and we will see the difference. Okay, back again. Now I've connected the motor to the wheel angle sensor, so that should spin as a unit. And as soon as we hit drive, there, you see the way it just slammed in. We've got a proportional gain of 200. It should be oscillating all over the place. But making the thing slow down, that makes a huge difference. If we do it the old way, like where we just have a single max pulse width modulation, and now make a change, see, there's that traditional wugga, 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 wugga. Especially if we start adding a little bit of min pulse width to compensate. There, see, it just wiggle, 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 wiggle. Yeah. But as soon as we slow down the bottom end when the error is 0, we slow the world down. Well, still does it a little bit. You can slow it down some more. There, see? It just eliminates that overcorrection, that overdriving it. You can actually turn the min pulse width right down now. See, and it's still only one error. Actually even works better. So, and if you want to go faster, the full capability of the motor, see, look at that. Just slams right down right here on the chart. Just slams right down. So it is a much more controlled way of doing it. And it's very, very fast. So again, if we tried to do that sort of speed up here and a high proportional gain, well, you know exactly what's going to happen. You get the wigga, wagga, 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 wagga. It's amazing that it even stops. But if you start doing less counts per degree now, that's exactly what you get. The dreaded oscillation. So if we go back here now, look at that, just calms it right down. And we still get, and it's still pretty wiggly, but slow it down even more. But everything's cranked. I mean, it's a little tiny motor. Do a little more conservative estimate here. Yeah, see? Well, a little faster. See, you just got to play with it. Like in your tractor too. As you move these up and down, do what works. You know, maybe that is still too high. There, pretty good control system. You get the speed. So you get the speed and the control. So give it a whirl. It is very different. and a little bit different way of looking at it. But now you can control when the error is high, and you can control when the error is low, and you get that nice mellow steering. The best steering I ever had is when I first built this, I had a really slow motor. There's no way the thing would ever do U-turn, but the motor turned really, really slowly, and it was a motor from an X-ray collimator, is what it was, and had like a 4-inch wheel on it. But it was a precision DC motor, multi-brush DC motor, and that thing steered perfectly because everything turned at the right speed, and it turned slow enough, and it had really good control. You could literally move the steering wheel a millionth of a degree and it would compensate. And I think what this does is it kind of brings back both worlds, where we can do the LowMax pulse width modulation to get the thing to behave when the thing is close by instead of oversteering. Because remember, when you're steering a vehicle, as you get closer to the line, you move the vehicle and point it in the direction of the line. But as you get to the line, then you want to steer the other way. And that's a crazy control system, in that you have to go the wrong way in order to go the right way. And if the steering wheel as you get closer to the line, if the steering wheel reacts too fast, then you're constantly going to be crossing back and forth over that line. The other thing I'm going to work on it this summer is the concept of an integral error, where here. Let's set it up and do that. There. See, we maintain that error of a half a degree, and it'll never get there. It'll just sit there and sit there. And now we got this half a degree. What an integral term does is, it says, okay, I get half a degree, so I'll take a little chunk of that. I'll take 10%. So that's 0.05. And then 1/100th or 1/10 of a second later, it still sees an error of 0.5. And it takes 10% of that. Now it's 0.1. And every frame, it keeps adding up, and it'll add that to the pulse width modulation. So 0.1, 0.2, 0.3. So it'll keep adding that up, and eventually, right, it just integrates to the line. Now our error is really, really small. But the trouble I found with integration is it's really tricky, because now you start steering the other way, and then you cross over the line the wrong direction again. Now the integral takes you too fast and too far over the line, and now you have to integrate the other way. So then you need a fairly fast integration. So kind of going in circles with the integration thing. I mean, I totally understand the concept that you take a little portion of the error and add it back into your pulse width modulation to get you closer to try to eliminate, that sort of thing. Like eliminate this error. That's what you're doing with an integral, is just getting the thing close to the line. It sounds simple in theory, but in practice, you just end up oscillating over the line back and forth again. And perhaps this LowMax in tandem with the integral, that might solve a lot of issues, because now we're limiting the speed of the motor to that compensation back to the line. And if the integral builds up slowly and we steer slowly, then maybe that combination will get us to the line without actually going over the line. And if we're within a degree or half a degree, then we just kill that integration value and it has to start up again. But yeah, steering is tricky. So, okay, a little bit of a longer video again, but I hope you understand what the high and the low max is now. Okay, thank you.